Ever, like, jumped off something really high? I'm not saying you had to, but you know that feeling, right?
Right.
Like, that stomach drop. That's gravity. Just showing off a little.
It's always there, isn't it?
It really is. And today, we're going deep on gravity. And we've got physicist Claudia de Rham's work as our guide.
Yeah, and what I love about de Rham is how her own adventures, like not just equations, really shaped how she sees this force we all feel.
Okay, so we've got, like, a stack of de Rham's talks, articles, all that good stuff here. So what's the mission for this deep dive? What are we hoping to uncover?
I think it's about uncovering this, like, surprisingly human side of physics, and we're using gravity as, like, our lens, because de Rham's journey, going from almost being an astronaut to tackling these huge cosmic mysteries, it shows how much science is driven by passion and just, like, not giving up, not just cold, hard logic.
All right, I'm intrigued, I gotta say.
Huh.
So how does a physicist end up almost in space?
So de Rham talks about how she was always drawn to experiences where you're completely immersed in something bigger than yourself. Like, she loved skydiving, scuba diving.
While feeling that weightlessness.
Exactly, that surrender.
And those feelings, they actually, like, informed her scientific work.
Oh, absolutely. I mean, she even trained to be an astronaut with the European Space Agency.
Whoa, seriously?
Yeah, and get this, she made it incredibly far. Like, down to the final 40 out of thousands of applicants.
It's cutting it close. So what happened?
They discovered a latent TB diagnosis. It disqualified her.
Oh, wow.
Heartbreaking. But even in that, in that setback, she saw this parallel to the entire scientific process itself.
Okay, I'm listening.
Setbacks happen, you get unexpected results. It's all part of the journey, right? Like, discovery doesn't follow a straight line.
It's like that saying, it's not the destination, it's the journey.
Yeah.
But in this case, the journey is understanding the entire universe.
Exactly. And speaking of journeys, let's go back to that feeling of free fall for a sec. De Rham talks about this a lot. It's not just a thrill. It actually reveals something really mind-bending about gravity.
Okay, I'm ready to get my mind bent. Break it down for me.
So think about how it feels to fall. You get that rush of weightlessness.
Yeah.
Why do we feel weightless when, like, we're clearly being pulled down by, a pretty strong force?
It's true. It's like, I know I'm falling, but it doesn't feel like I'm being pulled. It's more like, I don't know, floating, even though it's the opposite of floating.
Right. And that's because gravity acts on literally every atom in your body equally. So there's no one single part of you that's being stretched or pulled more than any other part.
Oh.
It's like being, like, completely enveloped in gravity's, like, embrace.
So it's not that gravity disappears. It's just evenly distributed.
Exactly. Think of it like being in a pool. You've got the water pressure all around you, right?
Yeah.
So you feel weightless.
Okay, that makes sense.
And this equal pull idea, we've got proof.
Is this where the Apollo 15 moon landing comes in?
Ah.
Because I vaguely remember something about a hammer and a feather.
You got it. That super famous experiment where the astronaut drops a feather and a hammer at the same time and they land simultaneously.
Right, right.
It's a perfect demonstration of what we call Galileo's equivalence principle. In a vacuum, objects fall at the same rate, no matter how heavy they are.
So whether you're a feather or a hammer, gravity treats you the same. That's pretty wild when you actually stop and think about it. And what's even wilder is that this, like, seemingly simple observation, it actually has these huge EE implications for how we understand the universe works. But before we get to that, all right, so we've got this whole equivalence principle thing. Things fall at the same rate, yada, yada.
Yeah.
Where does Einstein fit into all this?
Okay, so this is where things get really, really interesting. Because Einstein's theory of general relativity, as, like, groundbreaking as it was, it kind of hints that it might have some limitations.
Hold on. Are you saying Einstein, the guy who, like, redefined gravity for us, might have gotten some things wrong?
Not wrong, exactly. More like incomplete. Like, it works incredibly well in most scenarios, but then it starts to break down when you look at the extremes.
Extremes,
Like, think about what happens inside a black hole, where gravity is just, like, unbelievably intense, or when we try to explain why the universe is expanding and expanding faster and faster.
Okay, those DOs sound pretty extreme. Let's take those one at a time, though. Yeah. So black holes first. What's going on there?
So black holes, right. They're these regions in space where gravity is so strong, literally nothing can escape, not even light.
I knew that.
And de Rham explains, like, if you were to get too close, the gravity would be so powerful it would basically stretch you out, like spaghetti.
I think I'll admire black holes from a safe distance. Thank you very much. But how does this spaghettification, as fun as it sounds, show that Einstein's theory, like, needs work?
So At the very center of a black hole, you've got this thing called a singularity. It's like, imagine all the mass of a black hole crammed into a single point. Infinitely dense, zero volume.
Ouch.
Our current laws of physics, including general relativity, they just can't handle that. It's like the universe is saying, nope, my rules don't apply here.
I mean, I guess even the universe has its limits.
Right. Okay, now on to that other cosmic puzzle. The expanding universe. And to understand why this challenges Einstein's theory, we need to talk about something called the vacuum catastrophe.
Okay, vacuum catastrophe definitely sounds intense. Lay it on me. What is it?
So it all starts with quantum mechanics, which, tells us that empty space, what we call a vacuum, isn't actually empty.
Wait, what?
Yeah, instead it's like buzzing with all this activity, like virtual particles popping in and out of existence.
Hold on. Empty space isn't really empty.
Nope. It's pretty wild, right?
It's blowing my mind a little bit, not gonna lie.
And here's the catch. These quantum fluctuations in the vacuum, they should be creating a ton of energy. Way more than what we actually observe in the universe.
So if empty space is this, massive energy source, why isn't the universe expanding even faster than it is?
You got it. That's the paradox. Our current understanding says that this vacuum energy should be making the universe fly apart at, an unimaginable rate, but it's not.
So what's the solution? Is our understanding of particles wrong? Does Einstein's theory need a complete do-over?
That's the million-dollar question. And de Rham, she thinks the answer might be in how we understand gravity, specifically how gravity acts over, huge distances. She's proposing this pretty radical idea. What is gravity, kind of like the weak force in particle physics? What if it has a limited range?
But are you saying gravity might not be infinite? Like it could just weaken over really, really long distances?
That's the idea. And it's not as crazy as it might sound. Even giants in the field, like Pauli and Salam, known for their work on quantum mechanics and the Standard Model, even they consider this as a possibility.
Okay, so it's not like this idea came out of nowhere. But how does making gravity finite like that, how does it solve these cosmic conundrums we've been talking about?
So let's think about the weak force for a sec. Unlike gravity and electromagnetism, which seem to act over infinite distances, the weak force is confined to super short ranges. Like inside the nucleus of an atom, that's it.
Okay, and we know this because?
Because the particles that carry the weak force, they have mass. They're like heavy messengers that can't travel very far.
So if gravitons, those theoretical particles that are supposed to carry gravity, if they had mass?
Exactly. If gravitons have mass, it would mean gravity weakens over these huge cosmic distances, which could explain why we don't see the universe, completely flying apart from all that vacuum energy.
You know what? That is a pretty elegant solution. But if these, physics rock stars already considered this, why wasn't this whole massive gravity thing embraced sooner?
There was a pretty big problem. Previous attempts to make gravity massive always ran into these, inconsistencies. They would lead to these things called ghosts.
Ghosts. You got to explain this one.
So imagine ghosts like these phantom particles that have negative energy and they just mess everything up, like the stability of the universe. Out the window, everything goes haywire. Not ideal.
Yeah, that doesn't sound good.
Not at all. So it wasn't just a matter of saying, okay, graviton, you have mass now. It had to be done in a way that didn't, break the entire universe.
Right. Makes sense.
And that is where de Rham and her collaborators, they made a huge leap. They found a way to, tame these ghosts. For the first time, massive gravity was a viable theory.
That's got to feel good.
Yeah.
To, solve a problem like that.
Right. A major breakthrough for sure. But like any new theory, it needs to be tested, and that's where gravitational waves come in.
Ah, those ripples in space-time. How did those help us figure out if gravity actually has a mass?
Think of gravitational waves like messengers, and they're coming from the most energetic events in the universe. If gravitons have mass, these waves would travel differently depending on their frequency.
So, a higher frequency wave would behave differently from a low frequency one.
Exactly. And we have these future space-based observatories, like ELISA, that are being designed to pick up those subtle variations. They're our best bet for figuring out if gravity really is infinite or if it kind of fades out over these massive distances.
So we've learned so much, but there's still so much we don't know. It's like a cosmic detective story or something.
Totally. And speaking of uncovering hidden truths, de Rham makes this really fascinating comparison between these overlooked parts of the universe, things like dark energy, and the role of underrepresented groups in science.
Oh, yeah. I wanted to hear more about that. What's the connection? Okay, back to this analogy you were saying. Dark energy and underrepresented scientists. How does that even connect?
So de Rham talks about how, like, now we're realizing how important dark energy is, right?
Even though we can't even see it.
Exactly. And she says there's this whole, like, hidden potential in science, too. If we ignore scientists from certain backgrounds, we're missing out on all these different ways of seeing the universe, their talents.
Like, we need all hands on deck to figure out these mysteries, right?
Totally. de Rham says that a more inclusive science community, where everyone feels like their voice matters, it just leads to more creativity, more breakthroughs. It's about recognizing those dark energy thinkers who might have the next big idea, but maybe haven't had the chance.
And she's totally right. Think about, like, Jocelyn Bell Burnell.
Yeah, pulsars.
Discovering pulsars as a grad student.
Huge discovery.
Huge. And she didn't even get the Nobel Prize for that work at first.
It's crazy.
It just shows you that brilliance can come from anywhere. So we've got these potential breakthroughs in physics, but then also this call for more diversity in physics, in the field itself. Man, it's a lot to think about.
It really is. And even with all this stuff we've learned about gravity, there's still so much we don't know. Like, de Rham leaves us with some pretty big questions. Can we ever detect individual gravitons?
I mean, given how weakly they interact with, like, everything, it seems impossible, right?
Yeah, it'd be incredibly hard. But the whole search for the graviton, it drives so much research in physics. It's like the holy grail, of understanding this fundamental force.
I get it. And what about, like, the Big Bang?
Oh, yeah.
Does this whole massive gravity thing, does it change how we view the very beginning of everything?
Another great question. And this is another one of those areas where our current models, they kind of struggle.
Right.
The extreme density, the heat, those first few moments, total mystery. We're a long way from a complete picture, but theories like de Rham's, they give us new tools, to explore what might have happened way back then.
So it's like, even without a time machine, we can still try to put that puzzle together.
Exactly. That's theoretical physics, right? You're pushing the boundaries of what we even think is possible. And sometimes, when you're looking for one answer, you find even bigger questions, Speaking of which, remember when de Rham said gravity might have a sense of humor?
Yeah, I wanted to ask about that. What does she mean by that?
I think it's about how unexpected gravity can be. It's like, just when we think we're close to figuring it out, it throws us a curveball. Black holes, the expanding universe, could gravitons have mass? It keeps us guessing.
So I guess the real lesson here is our pursuit of knowledge, it's like gravity itself, full of twists and turns.
Perfectly said. We're driven by this deep need to understand, the universe, our place in it. Even when we stumble, we get back up and we keep searching. We keep exploring.
And maybe, just maybe, gravity, with a little cosmic wink, will lead us to even more mind-blowing discoveries in the future. Who knows? So next time you feel gravity pulling you down, just remember, there's a lot more to it than meets the eye.
It's this force of nature. Yeah, but it's also a source of, endless wonder, right?
Yeah.
And it's a good reminder that the universe is full of surprises.
And who knows what other things in science or even just in our own lives we might be taking for granted, things we just assume are true. Maybe it's time to question those things, dig a little deeper, and see what we find. That's what it's all about.